Welcome to a video on angles and their measurements. In trigonometry, understanding angles and their measurements is a pretty important topic. So let's dive right into it. So if you don't know by now, but the three main trigonometric functions are sine of x, cosine of x, and tangent of x. But what are the inputs to these functions? What are the outputs to these functions? What do these functions even do? Well, hopefully if you keep up with watching my videos, you're going to learn all about that. But this video is all about the inputs. The inputs, the values that go into sine, cosine, or tangent are angles. So what are the inputs? Angles, which is why this video is all about angles and their measurements. Now, I will briefly talk about what the outputs are. The outputs are numbers, real numbers, but we're going to save that for another video. And what do these functions even do? Like, okay, I plug an angle in here and out comes a real number, but what's the connection between the angle I plugged in and the real number that comes out? Well, guess what? There's going to be another video over that as well. But I really want to focus this video on angles that go into trigonometric functions. So let's do a deep dive into angles. So first off, angles need to be in what's called standard position. In the coordinate plane, an angle is in standard position when the vertex coincides with the origin and one ray corresponds or coincides with the positive x-axis. The other ray is called the terminal side. Positive and negative angle measures indicate rotations from the position x-axis in the counterclockwise and clockwise direction, respectively. Angles in center position that share a terminal ray differ by an integer number of revolutions. All right, there's a lot to unpack there. So let's just start off with what the heck standard position is. So as it said, and maybe you want to pause and go back and read that paragraph 18 more times, but what it said is that an angle in standard position has a vertex that is at the origin of 0, 0. So you always have to have a vertex at the origin. That's just being in standard position. Then one of the rays, one of the sides of the angle, must be the positive x-axis. Always. We actually call that the initial side. Initial side. The initial side of every angle in center position must be the positive x-axis. Then the angle goes, well, around, right? Now, if an angle goes in a counterclockwise direction, like this angle, we consider that to be positive angle. An angle that goes in a clockwise direction would be a negative angle. Now, what I want you to notice is that the two angles I just drew, one in blue, one in green, they have the same terminal side. The terminal side is the end of the ray, right? The initial side is the ray that starts on the positive x-axis. The ray that ends is the terminal side, and terminal means ends. So hopefully that makes sense as to why that's called the terminal side. Now, what I want you to notice about the green angle and the blue angle is that one is positive because it's going in a counterclockwise direction. One is negative because it's going in a clockwise direction, but they both end at the same terminal side. We actually have a name for that. Those are called coterminal angles. Coterminal angles are any two angles that end at the same terminal side. All right, the other cool thing about this setup is that angles are allowed to go around as many times as we want. We're not trapped into one revolution of a circle. So we could actually start here. All angles start on the positive x-axis, and we could go all the way around one full revolution, and then a little bit more to end at that same terminal side. So once again, now I have three angles drawn, green, blue, red, that all share the same terminal side, and they're all coterminal. And they're all differentiated by one revolution. So again, the green and the red angles are just one revolution away from each other. The green is, a proportion of one revolution, where the red is a full revolution and then that same proportion as the green. Okay, so hopefully you are slowly beginning to understand that big paragraph because I know there's a lot to unwrap there. But again, the bulk of it is this. all angles in standard position have two rays and a vertex. Vertex has to be the origin. The first ray, called the initial side, must be on the positive x-axis. And then where the other terminal side ends, well, it all depends on the angle. So here's another example where the terminal side ends down here. Once again, I could go in a positive direction to get to that terminal side, or I could go in a negative direction to get to that terminal side. But guess what? I ended at the same terminal side, hence they're coterminal angles. And I'll even give you one more. I could start on the positive x-axis and I could go all the way around 1, all the way around 2, and then all the way here for that same terminal ending spot. So I went 2 full revolutions and then a little bit more to end at that same terminal side. All right, so hopefully that gives you a strong indication as to what that paragraph said about angles in standard position, positive, negative, and then coterminal angles. So here's just another quick idea. I just want to make sure I put this down for sure, that coterminal angles are any two angles that share a terminal side. And if you think about it, every angle drawn in standard position has an infinite number of coterminal angles, because you could just keep going around and around and around and around and around the circle to find more and more coterminal sides. So again, I really want to make sure I demonstrate that, right? So there is a small acute angle, positive acute angle that just goes right up to that terminal side. But I could also go all the way around to go there. That'd be 1 revolution plus a little bit more. And I could do another one that goes around 2 revolutions and then plus a little bit more. Those are all examples of coterminal angles. And of course, those were all positive because I went in a counterclockwise direction, but I likewise could go in a negative direction and get another coterminal angle and another coterminal angle. You see how the options for coterminal angles are really limitless, and they're simply differentiated by 1 revolution. So if I have an angle and I simply add a revolution to it, I'm going to be coterminal. Or even if I subtract a revolution or multiple revolutions, I'm going to continue to find coterminal angles. Now, before we move too far, let's talk about naming angles. So here, let me just draw this simple acute angle right there, positive in ending in that first quadrant right there. Now, typically, if we don't know an angle's measurement, well, if we don't know something in math, we usually use a variable. So we could use x, y, b, a, c, whatever. But the Greeks were the ones that really kind of started analyzing this idea of angles and their measures. So we typically use Greek letters to represent the measure of an angle. So the most famous Greek letter we typically use is theta. It's kind of a slanted O with a line through the middle like that. So that is theta, T-H-E-T-A. It's a very common variable. Again, it's just a Greek letter. It's no different than an English letter, just a Greek letter. Other ones we use are alpha. Alphas are another very famous symbols for angles. So it's like I don't even know. Actually, it's really more like it really does supposed to look like an A, but it just kind of has this like elongated part at the top and bottom. Then we got beta. Beta looks like a B, but this front tail right here is a little bit longer right here. But anyway, you don't have to use Greek letters if you don't want to, but I will be honest, a lot of times you're going to see theta as a Greek symbol for an angle. Okay, now let's talk a little bit about measuring these angles, because I hope that you understand what an angle looks like, especially in standard position. But what is a way that we could measure that angle? Well, this is where we actually have a little problem. It's kind of known as the problem of angle measure. So here's the idea. I've already got done saying in the very beginning that the input value in a trigonomic function is an angle measure. Angles go into trig functions, and the output is a real number. But believe it or not, this actually poses a big problem for us if we choose to measure an angle in degrees, which is probably what you, watching this video, are way more familiar with. Everybody knows that 180 degrees is half a circle, 360 degrees is all the way around a circle, 90 degrees. You guys have been working with degrees since you were little kids, so you know what that represents. But there's actually a problem in that. See, the problem is that degree units have no mathematical relationship whatsoever to linear units. I mean, there are 360 degrees in a circle of radius 1, and there's 360 degrees in a circle of radius of 100. 360 degrees was just a number that the Greeks came up with that, honestly just sounded nice, and a lot of numbers go evenly into 360 degrees. I mean, imagine if all those decades and centuries ago, somebody said, oh, I think there should be 400 degrees in a circle. Well, then we'd all be using 400 right now instead of 360. So the actual angle measurement of what a degree represents truly has no meaning whatsoever to the relationship of linear units, which is measurements of length. So, a circle's size is truly dictated by its radius. Bigger circle, smaller circle. But like the radius, that's going to be another unit because radius is measured in, feet, inches, meters, centimeters, whatever unit you would like to use for the linear measurement would be what you would use for the radius. But that means that a radius has a linear measurement, feet, miles, meters, what have you, and an angle has a degree measurement, and that doesn't seem to work. So we came up with a better way. So it's actually way more natural. It might not be to you yet, but hopefully it will be someday at some point. It's more natural to think of the angle being determined by the arc rather than the arc being determined by the angle. That might have blown your mind, but read that again if you need to. A bigger arc means a bigger angle. Smaller arc means a smaller angle. So it is the arc that runs the show, not the angle, right? So again, imagine I have my angle in standard position right here. I'm just kind of drawing that in standard position. And I have this angle right here that I'm calling theta. If I want to think about how best to measure that red angle that I just drew, it makes way more sense not to pull out some random protractor that who even knows where that came from, but to actually think about, okay, if I were to extend this, just to kind of think about it in terms of this picture, right? If I were to think about this angle tracking as I swing it up from initial side to terminal side, if I were to think about the size of that arc, a bigger arc means it's a bigger circle. If the circle was smaller, it would have a smaller arc. But notice the angle doesn't change. Or let me even kind of give a medium one here. Medium circle, medium arc. The angle does not change, even though the length of the arc, whether it be the red, the blue, or the green arc, that doesn't matter. The angle is the angle. The size of the arc relates to the size of the radius, because the length of the arc is measured in the same unit as the unit of the radius, right? If I were to say, hey, let's measure the radius of this green piece of pizza here, right, or this green circle, the radius would be this value right here. And I could pull out a ruler to measure that in centimeters, feet, inches, whatever. Or I could do the red, or let me go blue first. I could do the blue radius. I could actually measure that. And then same thing with the red. I could actually measure how long that radius is. So it makes way more sense if I measure the angle, not by pulling out a protractor and using degrees, but I look at the relationship between the arc created and the radius, because those two things are both distances, which means they have the same unit. This idea, this thought of how to measure an angle, not by using degrees, but to look at the arc and the radius, this inspired what's known as a radian measurement. You might not be nearly as familiar with measuring angles in radians, but by the end of this video, you'll have a pretty good idea of what that is. And as we practice more, you'll have a really strong conceptualization of what that is. So let's talk a little bit more about radian measurement of an angle. The radian measure of an angle in standard position is the ratio of the length of the arc of a circle centered at the origin, subtended by the angle to the radius of that same circle. Whoa, okay, hold on. Like, I get it. That's a little bit confusing. So let me try to help you out here. Okay. If I think about a radius, and let's make the radius, I don't know, just some arbitrary number, we'll just call it R. And if I take that initial side and I start to swing it around, and I will, of course, create a circle if I swing that radius all the way around. But if I were to have stopped, let's say right, I don't know, here, stopped right here, then I could create my terminal side, and of course I have an angle. We'll call that angle theta. So what we're saying here is that a radian measurement is not what a protractor says based on degrees. A radian measurement for that angle theta is looking at the relationship, the ratio of the length of the arc created and the radius. In fact, the angle theta is equal to the length of that arc, which we call S. S is just the variable I'm going to use for the length of that arc that I highlighted in yellow there, divided by the radius. That is how you measure an angle in radians. You look at the arc length that the angle created, and you divide it by the radius of that circle. That is how you measure in radians. This is an angle measured in radians. And it makes so much sense because it's conceptual. Like you can actually understand that S and R are two measurements. The ratio of those measurements is your radian measurement. Easy. So the only other vocabulary term I want to make sure I explain to you is a subtended arc. It's kind of a weird word. I actually don't really like it. But the subtended arc is just what I have highlighted here in yellow. It's just the arc that is created from the initial side to the terminal side of the angle. We call that the subtended arc. And to find the radian measurement of that angle, you take the length of that arc divided by that radius. Now, this unit of radians, or this measurement style of radians, is the preferred measurement when it comes to angles. So if I go all the way back to the very first slide that we talked about here, we talked about what goes into a trigonomic function. What goes in is an angle. And I'm telling you right now, we prefer that that angle be measured in radians. All right, so a central angle of a circle has a measure of 1 radian if the angle intercepts an arc with the same length as the radius of its circle. Okay, I'm not trying to confuse you. Here's what I'm telling you. A formula to find a radian measurement, you take the length of the arc divided by the radius. All I'm saying here in blue is if the length of your arc and the length of your radius are equal, then you're going to get 1. If the length of the arc and the length of the radius are equal, 5 and 5, 10 and 10, 6 and 6, you're going to get a 1 radian measurement. So if I were to take a piece of string and lay it out across my radius, and then lift up that piece of string and lay it out across my circle, creating an arc, where that piece of string ends is where I have 1 radian. 1 radian is when the length of your radius equals the length of your arc. So if you have 2 radians, all that means is that your arc length was double the radius. 2 radians. So for example, if the length of my arc was 10 and the length of my radius was 5, then that means the length of my arc was double the length of my radius and I'd have 2 radians. That's probably going to happen somewhere over here, where if I again take that green piece of string and lay it out a second time, boom, I'm going to have 2 radians. So radian measurement is the ratio of an intercepted arc length divided by its radius. Here is that ever important formula. And when you get 1, that just means you have 1 radian. So here is a nice writing. My handwriting's terrible, of course. So this is a nice way of me saying, hey, an angle in radians is the length of the arc divided by the radius. It's that simple. Now, there's no units on radians. No units, because they actually cancel out. Because if your arc length is in inches and your radians and your radius is in inches, that unit will reduce and be gone. Or if you measured it in feet, well, they're both in feet and they're going to be gone. So that's actually a good thing. It makes dealing with radians really cool and really simple. It's not some like just random concept that some Greek philosopher came up with hundreds of centuries ago about degrees. I mean, who even knows what 1 degree even comes from? But we do know where radians come from. Better because radians take into account the relationship because radiuses of the circle and the length of the created arc. They really are the best. Here's one more viewpoint of this idea of arc length that's trying to give you another way to note it. Remember, 1 radian is found when the R equals the S. Now, through this formula, for a radian, we could actually solve for the arc length as well. Remember, S is the variable that we use for arc length. So if I just multiply the R over, multiply each side by R, I get that R times theta equals the arc length. So it's, again, just solving for the variables in the problem, right? Pretty simple, pretty cool. Just another viewpoint of how we can understand the relationship between the length of an arc and its radius. All right, now let's actually examine a full circle. This is the last thing we're going to do in this video here, just to really examine a full circle. So let's try to make sure we understand this, right? I'm going to say that this circle has a radius of r. Now, who knows what that radius is, whether it's 1, 2, 3, 4, it doesn't matter, right? But here's this, right? If we were to look at a full circle, starting at our initial side, going all the way around and ending right where we began. So this would be an example where our terminal side and our initial side are the exact same thing. Now, everybody knows that's 360 degrees, but how many radians is that? Well, let's follow the formula. Radians is the arc length divided by the radius. Well, I don't know what the radius is. I'm just calling it r, so I'm going to leave the radius r. But what's the arc length of an entire circle called? Oh, hopefully remember that from geometry class. That's the circumference. The arc length of an entire circle is known as the circumference. And I hope you remember the circumference of a circle is 2 pi times r. So if I'm trying to find the radian measurement of an entire circle, I'm going to take the arc length of an entire circle, 2 pi r, and divide it by the radius of that circle. But something really cool is going to happen. Those radiuses are going to reduce to 1. Whether they are both 5 or both 16 or both 7 or both 3 or both 0.9, they're going to reduce to a 1. And I get, no matter the radius of a circle, there are 2 pi radians in a full circle. So just like there's 360 degrees in every circle, regardless of its size, there's 2 pi radians in every circle. Now that's approximately 6.28, but officially, exactly, it's 2 pi. Now, if there's 2 pi in a full circle, well, then that means that there is 1 pi in a half a circle. So if I take an array and I go all the way around to a half circle and I end, I just created 1 pi radians. And that means a quarter of a circle, starting right here on the positive x-axis and going up a quarter, would be pi over 2 radians. That would be 1/4 of 2 pi. So 2 pi is the full circle. A quarter of that would be pi over 2 once it all reduces out. So we have 2 pi as a full circle. Pi over 2 is a quarter of a circle. 1 pi as a half a circle. So this would be 3/2 pi down here. Makes a lot of sense, right? I hope. Now, we also know that 360 degrees is a full circle. So a conversion factor would be that 360 degrees would be equal to 2 pi radians. Or we could reduce that. 180 degrees is equal to pi radians. So there is my conversion factor between radians and degrees. 180 degrees, old school kind of, I was just going to say it, dumb way of measuring an angle, would be equal to pi radians. So again, if you need to replay this section to really understand how I did that, I just generically called the radius r, and I said, let's look at the whole circle. The whole circle has an arc of 2 pi r. Take that arc, divide it by r, the r is reduced, and you just get 2 pi. So just like 360 degrees in any circle in the world, 2 pi radians in any circle in the world, which means there's pi radians in a half a circle. All right, that's it for this video. I hope you understand this idea of measuring angles. And if you're still trying to figure out why is he explaining to me about measuring angles, because if we go all the way back to the beginning, what goes into a trig function is an angle. There's going to be more videos about the outputs, and there's going to be more videos about what these outputs even come from. Like, what's the connection here? But stay tuned for more videos. This video was simply about angles and the proper way to measure.